fun to be back again today with William.
Yeah.
I just actually one just published today of our last conversation.
Okay.
And so then this is a good time to be talking again. So we have one to put in the stack for next month. Before I get started, I want to just remind everybody again, I'm going to be speaking at the face-to-face conference in Olympia, Washington. I'll put the information in the description, and that will be in the second week of September. And I'm very excited about that. There's a lot of good speakers: Chris Green, Michael Martin, Graham Pardoon, Paul Vanderklay, myself, and Sherry Suter is going to be there. I don't know if she's speaking. Nate Heil of Grail Country is the host of the whole thing. So I think it's going to be a spectacular event, and I'm really excited about it.
Yeah.
And what we're going to talk about today is measurement, one of my very favorite topics. And I thought it would be fun to talk to you about that because I know that you're in manufacturing, where measurement is extremely important. And you and I had just both recently watched this video, which I'll put in the description section, of Adam Savage talking about metrology. So maybe you could start us off by defining metrology.
Yeah, absolutely. Yeah. So when I was in college, one of the classes, actually the class where I got glasses, I'll never forget this. I had put it off for a long time because I was like, I can see fine enough. But it was a 7 to 10 p.m. class on metrology. And I was working while I was going to school. So I would work 8 hours, drive to school in the evenings, and then go to class. And I remember it was about the second weekend, and my eyes would get so tired from like eye strain from needing glasses that I couldn't read the instruments anymore. And that was the time when I finally actually gave in and got glasses. So it's a fun story. But I was taking this metrology class, and I thought one of the things that I remember most from my entire college career was something that the professor of that class started off with. He was a gentleman, must have been in his 60s. He had been doing things for a long, long time. He had worked with NIST. He had worked with some of these big companies that do measurements in metrology and things like that. And as we were watching the Adam Savage video, Adam Savage said, metrology is the science of measuring things. And that's how almost everyone will define it. It's the science of measuring things. So it's figuring out what are the best ways to measure things, what are the tools, what are the techniques, what are the processes, those types of things. But the professor that I had said something different. He said that metrology is the art and science of measuring things. And I've never forgotten that. And part of what he was pointing out is that every time that you measure something, you are a person measuring the thing. He talked about how every time you adjust calipers or a micrometer on an outside dimension, the amount of pressure that you're applying and the technique with which you apply it is an art that you learn how to do and that you gain skill and ability to do with time and experience. And as I've thought about this over the decades since I took that class, has deepened even. Because one of the things that I run into in manufacturing, especially in high production volume manufacturing, is automated measurements, right? So the machines themselves are able to take measurements via computer code that's given to them to set things up, to calibrate, to review. Things like CMM machines that run programs and stuff like that. Coordinate measuring machines, which are a very specific type of measurement equipment that that you hate using because they're expensive and they're slow, but sometimes it's the only way to measure certain types of things. Even there, where it's completely automated, quote unquote, right? The entire process, you load your piece and then you click measure and it runs a program. Even there, there is a person deciding what and how to measure, right? So your agency is itself kind of being the boundary or the container within which the measurement is happening. And so even there is an art to what is going on. There is a relational, personal aspect to metrology. So that is the basic idea of metrology is how do we measure, what are the tools, techniques, processes? It's a science. But my experience and understanding of it has included this aspect of art, or the relationality of it as well. And that was one of the things that I think the video itself was really emphasizing, without Adam Savage necessarily having a full kind of developed set of language around that concept as he was kind of working it out.
I loved what you said, that your agency is the container within which the measurement is going on.
Yeah.
Wow. I mean,
Yeah.
we're probably going to get into how that fits in here, but
Mhm.
that's fantastic. And regarding the art thing, maybe this would be a good time to do this, to share share Adam Sandler talking about guitars. Partly because
Yeah.
there's obviously, when you think about it, there's a lot of measurement going on with the guitar, because each string has to be at exactly the appropriate tension for the guitar to make music rather than just noise, right?
Yeah.
So let's take a look at this. And you see Adam Savage now, right?
Yep.
And tell me if you can hear this.
Almost certainly experienced it as well. So let's say you play the guitar. When you first picked up a guitar, it is a mystifying arrangement of tension, vibration, resonance, tonality, and you started noodling with it. But you didn't have any point of view about how stiff the strings should be or what the tonality should be. You were just playing. And then as you got better at playing the guitar, or any instrument you have learned, the kazoo, seriously, it doesn't matter. At a certain point, you get past the beginner mode and you start having points of view, and you start seeing what you can't do, and you start trying to burn new pathways to learn how to do those things you can't do. And at each stage, you are gaining new eyes. So if you are a longtime guitar player, you understand information just by gripping the neck of the guitar and putting your fingers into a chord. There's all sorts of information being transmitted to you about how flexible the guitar is, what kind of strings it has, what kind of experience you're going to have with it. And none of this is stuff you could have possibly surmised the very first time you picked up a guitar. It's only from the iteration and the practice and the experience that you gained the eyes to be able to understand a guitar at that level. Same thing with a camera, same thing with driving a car professionally. Archery, right? That each of these, every discipline that you would undertake, that you could undertake and become better at, involves you being able to see new heights, and it's climbing. It is climbing. Chaim Potog wrote a book called The Book of Lights, about the enlightenment of a young Hebrew scholar. And they talk about the progression of awareness of the scholar.
I'm going to stop right there just in case there's some sort of limit on how much they'll let me play from one of his copyrighted videos. But when he said every discipline, this is true of every discipline. Okay. And I've been saying for a while, and I think this video just enhances that even more, is that I think science does not take into account how much of an art it actually is.
Yes.
Right? Because and I think that there is a pattern to life. The way that we live life requires making little experiments every moment. Seeing how much we can push into the world in every decision that we make. And that's kind of how we calibrate our own space, our own personality, our own values. Everything is these little experiments, and where we develop a point of view. And every discipline is like this, and it requires this getting to the place where I am enough. There's enough distance between myself and the thing I'm doing so that I can, like, if you're learning to play the guitar, you have to learn exactly what all the chords are, exactly what the tension should be to get it so it's tuned exactly right, and all of that. So you have a distance from it. You have the scientific measurement of the process, and art is like that. You have to learn what different paints will do, and whether they will fade, and what the texture is, and the viscosity, and how it's going to react on the substrate, and all of that. Those are learning things. But then when you're a part of it,
Yeah.
you're an indistinguishable part of it. So
Yeah.
when you're playing the guitar, every guitar player, their finger is going to be on the string just a little bit different than somebody else. And maybe a little bit more pressure or a little bit less pressure, and the way that they strum it and the way that they pick it. This is why you can listen to some guitar player without seeing them, and you can say, oh, that's so-and-so,
Yeah.
right?
Yes.
So, and a scientist is also like this because they
Yes.
are a part of their measurement process,
That's exactly right.
right? It's indistinguishable.
Yeah, it's inseparable in our experience existentially. You cannot remove the scientist from the science that is being done. And part of the lie of science, as it is currently understood in post-Enlightenment Western thinking, is that the scientist doesn't exist, basically. It's that there is no person or personal aspect in what's being done when you're doing science. And it is a lie. And it's a lie in a certain sense where it can be an intentional self-deception in order to achieve a goal. But it's also, and that's kind of, I think, how it was originally understood. The idea was remove the person as much as you possibly can to try and get to something universal or applicable to any person. So for something to be applicable to anyone, you kind of have to not have a person be a contributing component to it. And that's the original conceit of science and one of its greatest strengths, because certain things in our experience are reliably repeatable in such a way that you can remove the person and it will still repeat with enough regularity that we can build skyscrapers, that we can create airplanes, that we can do all of these wonderful technological things that we can do. But the aspect of it that can never fully be removed actually goes back to what I was talking about, where your agency is a container, is that technology itself, it can shape our agency. It can push us in different directions by its own shape itself, as we're using it, like Vervaeke talks about. In order to hold a cup, you grasp it, and in grasping it, you are shaping yourself to it to some extent. Every technology is the same way. Every technique is the same way. In order to use this thing, you have to shape yourself to it to some degree, and that shaping will have an impact on you as the person using it. You are not independent of the technology that you're using, whether it's a different kind of science or whether it's a particular piece of equipment or anything like that. And when we don't properly recognize that, we're in danger of allowing it to shape us uncritically or without our own recognizing of the way that that's affecting us. And so that's where I get into a little bit of contention with this idea. Well, technology is neither good nor bad. It's how you use it. There's some truth to that, but technologies have shapes, and in relating to them and using them, they will shape us. And so sometimes that shape will push us more towards evil, or sometimes it will push us more towards good. And so even though you can subvert that, or you can overcome that using your own critical approach and your own understanding, tendency to push you towards evil for good, it doesn't mean it's not completely arbitrary. It's not completely separated out. It's a little bit, there's a more of a interplay there than I think often is given credit for when people say technology is neither good nor bad. I think it's too simplistic of a thing to say. And with what you're talking about too, I think even this word exactly is something worth considering, because exactly means within tolerance. Like, one of the things that I often joke about is we say often in English, yeah, it's good enough. It's good enough. You know what I mean? How long is it? It's 12 inches. It's a little more than 12 inches. You know, you're doing construction, you're doing a project for your house or something. You're building a shelf. It's 12 inches. It's 12 and a 16th. It's good enough. When we say that, what we mean in engineering language would be something like it's within tolerance. There's a certain amount of tolerance that we give. It can be, we're aiming for this ideal abstract concept of exactly 12 inches. But if we're within this much tolerance, it will serve the function for which we are making it. And And this is not only true in making physical things, this is true everywhere, where it's just like our lives involve leaving room for the tolerance of it can be exactly, but it's not the ideal. It's exactly meaning within tolerance of what we actually need to serve the function that that we're looking for from whatever it is that we're doing or whatever it is that we're making or things like that. And for good, I think the example of guitar and everything else that Adam gave and that you're talking about, and even paints and things like that, right? He's talking about you gather information from it, but I think that that's not the right language. I think you know it. You know it in a way that isn't even necessarily be able to be put into words. I mean, it is something that you know deeper than that. You know it relationally. You know it in a way that allows you to do things without necessarily even being able to put it into words, and yet you still know it in a deeper way. And I think that the way that Vervaeke's 4Ps kind of apply, there's some of that here and stuff like that. Whereas the exact language that Adam Savage was using in that video, he's like reaching after it, but doesn't have the language. And I think that you're absolutely correct that that's so important.
Well, I like the way that you said it's exact,
Yeah.
not ideal.
Yes.
And one of the ways that I think that gets illustrated in his video is that he's working with gauge blocks.
Yep.
And he starts out with his own gauge block set, which is, he has one that he bought that he could afford.
Yeah.
And I believe it's steel.
Yes, steel.
Is that correct? Okay. And
shop floor gauge blocks are almost always steel.
Okay, and we'll get into why that is.
Yeah.
So his gauge blocks are steel and they're affordable and they're fairly precise and they can be used for measuring a lot of things.
Yeah.
And then there's a set that he got as a gift that are super, super, super precise and expensive, and they're made out of ceramic.
Yes.
And I'm guessing it's that's because ceramic can be made smoother because of the kind of material it is. Because I mean,
it's not necessarily
looking at it with a microscope and you burrowed way down, wouldn't there be more fluctuation on the surface of steel than there is on the surface of ceramic?
Not necessarily more fluctuation. Both ceramic and metals, their molecular makeup is a lattice structure. So ceramics are typically molecules that are in the structure, whereas metals are typically especially primary element metals, like single element alloys. It's one element instead of a molecule. So the regularity of the structures, though, are the same of the lattices. Generally speaking, you have about 3 basic lattice structures, whether it's body-centered cubic, face-centered cubic, and then there's a hexagonal one that I can't quite remember, but off the top of my head, because it's been long time since I was in college, and I don't deal with those microstructures on a day-to-day basis.
It's not relevant here.
But it isn't. That's true. I apologize.
No, I'm the one that brought it up.
Yeah, but what you do get with ceramics is you get a couple of different things with ceramics over steel. He talked about one of them, which is temperature.
Temperature, yeah.
Yeah, and the coefficient of thermal expansion, or how much its dimensions change proportionally with each degree of temperature, is different. And so that's a good thing. One of the other things that you actually get with ceramics is you get very high hardness. So in material science, hardness and ductility are like inverse, they're opposites of each other. So typically. So the harder something is, typically the less ductile it is. Ductile is its ability to flex without breaking. So typically the harder things are, the more brittle they are. There are exceptions, but ceramics have a very high hardness. And one of the advantages of hardness is any impact or damage or load underneath a certain threshold, it won't move. But if you have something that's softer and more ductile, it'll deform. You can have an impact that leaves a mark, basically. And so one of the advantages of the ceramics is actually hardness.
So that takes the measurer out of the picture a little bit. So it's like no matter
Yes.
how hard you hold those calipers
Yes.
together, you're not going to deform it because it's
Right. It's
set
much
up.
more difficult, right? Because there is actually this reality in the physical world, which I love from a different class. Everything is a spring. And basically everything in the world, every piece of like physical stuff, like when it's solid, when it's in the solid phase, it acts like a spring under certain loading conditions. And so that means that it compresses and returns to its initial length when the load is removed. And that's true of plastic, that's true of a pen, that's true of everything. For almost everything, it's negligible. The amount that's true is negligible, meaning that it's imperceptible to, our daily experience. But one of the ways that you can kind of see it a little bit is like when you're on a floor that it's got long beams and you walk or drive something heavy over it, you see it flex. It's acting like a spring. It's flexing under the load. And then actually the way that you can describe that is the same equation that you would use for a spring's deflection. And then it comes back in an elastic way. And that's still true of ceramic gauge blocks. It's that the amount is less than the tolerance which you're getting, basically. You're minimizing it. Because one of the things, and he really talks about this a lot in the video, is that you will never eliminate completely tolerance from your measurement. That's not kind of how I would say it. That's not the language that he uses, but that's using my own language. You will always be able to say it is this precise with this much tolerance. And exactly what that is depends on your technique, your process, the equipment that you're using, and all sorts of other things. And I haven't looked that closely at the quantum physics stuff with Planck length, Planck distance, and stuff like that. But I don't know. I don't know that you can actually ever, in practice, eliminate that from your measurement or your experience of things. Like I think that there will always be that.
Even if you could, you can't eliminate us.
Exactly. And then
even
that's
if
part
you
of
say,
it.
well, I'm gonna outsource it to a machine. Yeah, but I built the machine.
That's right.
And the machine is built out of things that can't be 100%
Yes.
exactly precise, right?
Yeah, absolutely. And actually, that's actually one of the things. So in manufacturing, which is the industry that I work within, one of the things that makes components more expensive to produce and then to purchase necessarily is how tight of a tolerance you ask for on one of your dimensions. And so an example of this, then what I do, I work in casting, but almost all of the castings that I make get machined. And typically a casting tolerance is going to be looser or you have more tolerance than a machining tolerance because the casting process has less precision in it than the machining process. So like a typical casting dimensional tolerance might be like plus or minus 10 thousandths. And that's huge for like a machining, probably. I mean, it kind of depends on the machine, the material, and stuff like that.
It's like 1/10,000th of an inch or 1/10,000th.
So 10 thousandths would be 1/100th of an inch. So 1/100th of an inch in either direction. So
okay.
So yeah, 10 thousandths with a th at the end.
Okay.
Yeah.
So, but of an inch, not of a millimeter.
Of an inch.
Okay.
Well, which would be like what would that be? 10 thousandths would be like 0.25 millimeters, maybe. I'm not doing the math off the top of my head very well, but you could convert it into metric. I mean, maybe plus or minus a millimeter, plus or minus half a millimeter, depending on exactly what you're doing. But you can get some pretty wide tolerances for castings because you're dealing with solidification, you're dealing with mold variability, you're dealing with a lot of things that add like tolerance into your process. But for machining, we might say plus or minus 2 thousandths. So like 5 times tighter tolerance. For what I used to do at the company that I worked at previously. And that's pretty tight. That's like, you got to have your tool and your machine and everything really set up well to reliably manufacture parts within that tolerance. But we had a component that we bid very high and that took us extra time and extra energy to measure and to machine and to keep on top of, where our tolerance was half a thou. So it was a total range of 1/1000th, half a thou in either direction, or 5/10,000ths in either direction off of the nominal from the drawing. And we didn't have machines that were able to produce that without us reviewing it constantly checking on it. There are people who do. So one of the things that this kind of like goes into is how machines themselves, these automated machines that you say go to this many thousandths and machine this much and use this tool, they have offset for tool wear. They have all sorts of like loading sensors to determine whether or not it's deflecting, like bending or being a spring because of how hard it's pushing against the thing that you're machining. And all of those tolerances give you a tolerance range of your machine's accuracy, which the manufacturers of the machines provide. And as a rule of thumb, you want your machine's tolerance to be 1/10 of what your tolerance range is for your for your part. So if your tolerance for your part is 1/1000th, you want your machine to be accurate to 1/10,000th. And then you're almost never going to have to worry about the machine's tolerance putting you out of spec. But you can live with up to maybe 40%-ish before you start, not being cost effective. But there are machines shops here in Los Angeles where I live that they go to 1/1,000,000th of an inch with their machines. And these are extraordinarily expensive machines, extraordinarily expensive components, compared to the kind of things that I make, which are higher volume components. These are one-off type things for aerospace applications and things like that, or medical applications, which was also mentioned. And I mean, they're extraordinarily expensive. And then one of the other things, which I was really glad that Adam mentioned in the video, because I was really waiting for it. He got to it at about half an hour into the video, but is heat matters. The temperature. Those machines, the environment within which the machine is controlled to a certain temperature, and then they account for the temperature of the component while it's being machined, so that because machining, when you're making chips, you're breaking pieces off, puts heat into the workpiece and into your tool.
Mm-hmm.
And that's why you flood it with coolant and things like that, depending on different factors. They account for that, all of those things, in order to be able to hit those types of tolerances. And then, as also he mentioned, you have to measure it at a specific temperature, or else it's not going to give you the right amount, like the right measurement. And I remember, we would do that. We would have, oftentimes in manufacturing, you'll have a measurement room or a CMM room, and it'll be climate controlled to 68 degrees, because that's the standard via NIST, where 68 degrees Fahrenheit plus or minus, and that's the temperature at which you measure things. And sometimes the purchaser of your components will give you a temperature that they want to measure it at, and other things like that might adjust that, but that's the default in the standard. So there's so many layers of places where you play with it.
Yeah, so the first thing that jumped out at me from what you were saying is that the machine has to be capable of being much more precise than that which it is making.
That's right.
Right?
Yes.
And I'm guessing that works down through every level.
Yes.
Right. And if you look at it the other way around, like with life, let's say,
mm-hmm.
every level is homeostatic to the level that's above it.
Yeah.
So it's always seeking value.
Mm.
So the lower level is that right? The lower level is making decisions based on the value that's available at the upper level.
Mm.
Has to be something like that.
Mm.
Yeah, I have to work that out in my head.
Yeah.
I kind of feel like Kathy Newman.
Mm.
I have to work that out in my head.
Yeah.
But the other thing that occurred to me about the temperature thing is that I wonder if scientists have ever done a study of like test taking for people. If you're if they kept a standard temperature in the room of 68 degrees, would that even everything out so that you would always have the same mental capacity at a certain temperature? And when the temperature goes up and your body gets more distracted by the heat, does that affect your mental working? I'm guessing it really does. That the temperature affects not only our it obviously affects our physical ability to stay homeostatic. But I'm guessing it also affects our mental functioning and the physical functioning of our bodies and everything else, you know?
Yeah. I think being too far outside of the standard range, higher or lower, would definitely have a negative impact.
Yeah.
That I'm sure.
So one of the basics of what Adam Savage is talking about is that the closer you look at anything, the harder it is to measure, right?
Yeah.
And let me see. One of the things that he said is that he was talking about viscosity, and I thought this was so fascinating, right?
Yeah, absolutely.
Viscosity, we tend to think that you should be able to measure viscosity. Well, this is thick up to this level. You should be able to give it some sort of a number.
Yep.
But he said viscosity is a relationship to all of the environmental factors surrounding it. Viscosity is not a measurement.
Yeah.
I wonder if you could say something about that.
You can't simplify it to a number, is basically, I think, the main point that he was making there. You can't take all of what your understanding of viscosity is and then make a table and say, this is the number. And then by simplifying it to this number, I fully understand it. You're going to lose too much of what it is by simplifying in that way. And then that's going to be a big issue.
So let me tell you what I think he meant by that, and then you tell me what the more scientific approach would be and what I'm missing.
Okay.
Because it seems to me, if I'm looking at, I'll take something that I'm familiar with, and that's honey. And honey is very viscous, okay? But if I'm trying to pour honey out of a container at room temperature, it's going to pour, but it's going to kind of glop out of the container. But if the room is colder, then it's going to be much thicker and harder to get. It's going to be more like sludge coming out of the container. But if I heat it up on the stove, it's going to become almost as liquid as, say, coffee or something like that. And flow much more easily. So viscosity is certainly attentive to temperature. But I'm guessing it's also susceptible to pressure.
Yes.
And probably some other things that affect viscosity.
So some of so pressure is a big one. And actually also the surface of the container, the material of the container within which you're flowing also affects viscosity. And the surface roughness can be something that has an impact on what you actually experience as far as the viscosity goes. But pressure is actually a really interesting component of it. Temperature is one of the most obvious ones. He gave the example in the video of oil for your car, and how when it's cool, it has kind of one area like viscosity, and then when it gets hot, it has a different one, and that's one of the ways that all of those oils are kind of described when you're purchasing them and when you're using them and designing them and choosing them for a vehicle. But the pressure one is actually super interesting, because one of the things in engineering is you do fluid dynamics. And fluid dynamics is interesting because fluids include liquids and gases. Liquids and gases are both fluids in fluid dynamics, but they actually act differently in some ways. And one of the ways is actually with viscosity. So one of the things with liquids is that as you put more energy into liquids, they flow more easily. so they're less viscous, right? And you were describing that with honey. So putting more energy can be in temperature, or it can be pushing them with pressure, making them go faster. So speed, kinetic energy is one of the ways that this also functions. Putting more energy in generally makes them flow more easily. But gases do the opposite, actually. So air, which is one that I dealt with in molds. So I work in, we've talked about this in previous videos, in die casting. Die casting, we have steel molds that we're filling in the order of milliseconds. All of the volume of air that's in that cavity needs to get out of the cavity while the metal is coming in, or it's going to get mixed in with your metal, and it's going to create what's called gas porosity, which is going to reduce the mechanical properties of your components. It's going to potentially, when you machine away a surface of material, reveal like a cheese, like Swiss cheese, like surface. You don't want that. That's not going to provide the proper function. So getting the air out is a really important thing. And so one of the things that I learned very practically that I had been introduced to in my schooling is that when you put more energy into air, it flows worse. It gets more viscous. It doesn't flow as easily. And that's either temperature-wise, so the hotter the air is, it doesn't flow as easily, or when you're forcing it by speed. And then this also actually does, in air at least, has interaction with the speed of sound, where as air approaches the speed of sound, it stops being able to flow, basically, because of the way that sound and sonic boom type effects work. But basically, one of the things that we have to design and engineer in our molds is that the air is able to flow quickly, but not too quickly, because if it's too quickly, it stops flowing completely. And so you have this weird paradox of or tension between adjusting the way that the air is flowing in the mold. And so it really does depend on, like we were talking about, temperature, but how fast you're pushing it. And that has to do with kind of pressure as well. That is a pressure effect. And so, but I mean, it also has to do with material, and it has to do with the fluid itself, whether it's a liquid or a gas, and what type of liquid and what type of gas, because there are all sorts of other effects going in there. And so it just becomes so much more complex than we could ever fully describe. We could never get all the way down to an ideal, completely ideal, perfect understanding. So what we do, like we always do, is we make maps. We make an equation. We take measurements. We get we set the limits of what we expect to use it. We take measurements along that. We'll interpolate. We'll do calculations between, if it's between two things, as long as our measurements are close enough, we'll say it's going to be about this much. It's within tolerance if I approximate it using, these two table entries, and then just average across the proportional difference between those two things. And part of what this reveals actually is something that I remember going through. It was in my 400 level heat transfer class. When we think of science, we think of equations. We think of ideal. We think of no tolerance as we grow up and we're thinking of science, right? It's perfect. If it says 12 inches, it's exactly 12 inches. If it says this many degrees, point however many decimals we go out, that's exactly what it is. It's perfect, right? It's without error. It's without tolerance. That's the way that I grew up thinking about science. And I remember this viscosity is a great look at that same concept where it isn't actually that way. There isn't this magic number that's so perfectly and ideally describing exactly what viscosity is. You can get an understanding of it by knowing it and understanding all of the context and the circumstances and the relationships between what it is that's flowing and the things around it that you need to understand. And in so doing, you can know it well enough to relate to it, to create with it. I think actually Adam's topic of maker fits Tolkien's idea of sub-creator very well. But my experience of this, my first experience of this same reality was in heat transfer, because in my heat transfer class, I was going through these classes, I was reading this book, and I was so used to equations empirically, I mean, not empirically, but derived from first principles. this equation turns into this equation because we just know that this is exactly how the world actually is. And in my heat transfer class, a majority of the equations that I was learning were empirically derived, which means they went out and they took a bunch of measurements. They didn't fully understand exactly every minute detail of why things were going the way that why things were working exactly the way that they were. And then they fit an equation that kind of matched the data and said, this is the equation that we're going to use because it will provide us results that let us live in the world properly to achieve the goals that we want to do with either insulating, with whether it's HVAC or any of the other applications for heat transfer, keeping engines cool or computer chips or all of those types of things, keeping a house cool or warm, depending on the environment that it's in. These equations will allow us to do that job. But there's already tolerance, plus or minus, in the equations themselves because they're empirically derived. They're not derived from first principles in many cases. And that even goes to one of the things that you can do in heat transfer. You can act like it's like an electrical circuit with resistance. And the model fits really, really well. These different materials provide this much resistance to the heat transfer. You have this temperature differential, which is like your voltage potential. It's a potential energy transfer. And then you can do all of these equations and these mappings, but it isn't as ideal and perfect as we think of science, as I grew up thinking of science.
Mhm.
And that was actually my first experience where it was like, oh, this is something different than I thought that it was. Maybe there's more of the person in the way that we deal with this. Maybe there's less precision and perfection and understanding to the fine detail. Maybe we know less than I thought that we knew. Maybe would be a way to sum it all up. Yeah.
Two things jump out at me that I
Yeah.
want to ask you about.
Mhm.
Because now you're into thermodynamics, basically, when you're talking about
Yeah.
heat transfer, right?
Yes.
Because what came up for me when you were saying that liquids, when you add energy to liquids, they flow more easily.
Yep.
When you add
Generally
energy to
speaking.
viscous liquids, they flow more easily. That's obvious. When a car heats up, the oil goes through easier than,
Yes.
right? Okay. And adding energy, they always say that if you don't add energy, that things are just going to become entropic and just start to fall apart over time. Adding energy kind of turns things around and it becomes anti-entropic in terms of the way the world works, right?
Yeah.
So then that would seem to say that when a liquid becomes less viscous, it is more organized rather than less organized.
Oh, that's an interesting question.
Because then when you started talking about gases, when you add energy to a gas, as in pushing it or heating it up, that's a little bit easier to understand in terms of thermodynamics, because then everything is bouncing around and moving a lot. And that's why it becomes very almost pressurized when you add energy to it, right?
Yeah, of course.
And in some way, as long as there's a boundary around that, that's how form starts to take place and becomes anti-entropic when it's confined, when it's in a confined space, and you start adding energy to it.
Yeah.
Then you start getting anti-entropic.
Yeah. Well, pressure goes up, right? So if
you keep putting in more and more and more particles, eventually it's going to shape into something. It's going to become maybe it's going to be a crystalline structure or a lattice structure or something like that. It's actually going to organize, right?
Yeah. If you compress, you can. So one of the things that you can do to turn a gas into a liquid into a solid without changing temperature is pressure, right? So like so ideal gas law, PV equals nRT, basically pressure and volume are going to be proportional as they relate to each other to the mass and the temperature. And then there's a coefficient that adjusts it. But so basically it's pressure and volume together multiplied is going to give you mass and temperature. So when you play with any of those four things, the other ones holding constant, if you hold two constant and play with one, the other one has to move, and it'll move depending on which side that it's on, right? And so if you like hold temperature the same, and then you're increasing pressure, either the volume has to go down so that the equation stays balanced, or the mass has to go up, which is what you're talking about. Pushing more and more in would be a way to increase pressure, while holding a constant volume and a constant temperature. And so, yeah, and so as you're putting more and more in, either more molecules into the same volume, or if you're taking the total number of molecules and decreasing the volume itself to increase the pressure, then you can actually take gases and turn them into liquids or liquids into solids. And actually there is if for water, there's this really interesting thing where, because of the way that the phases line up, there's a triple point where at a certain temperature and a certain pressure, you can get all three phases mixed together, in kind of a static way, which is really weird, really weird. That's not normal. Normally you can get two for other things kind of mixed together, which is super fascinating. But yeah, it is, the question of entropy is one that's so hard.
Yeah, well,
entropy is.
I don't want to dig into that, because we can talk about that another time. But
it's a lot.
Yeah, I've thought about it before in terms of gases, but I'd never thought about it in terms of liquid. What happens when you add energy to a liquid? But anyway, so the second question is, you're talking about viscosity.
Yeah.
And earlier you were talking about how everything is a spring.
Yes.
And when you were saying everything is a spring, what popped
every solid
in my head was, oh, but some things are viscoelastic, meaning that they give way, and then some of the giving way stays given.
Yes.
It doesn't bounce back. And then when you said viscosity, I thought, oh, is that where the visco comes from in viscoelastic?
Yeah, I think they're definitely related. Yeah.
Oh, okay. Okay.
But every solid thing is a spring. So not liquids aren't springs, and gases aren't springs in that way.
Yeah, I was just thinking about solid things.
But one of the other things,
I don't know if you ever watched the video that I did with Richard Watson, where he's talking about his theory that life is a song.
Oh, okay.
And his whole theory, it's very, I mean, he's brilliant. He's a scientist and a computer geek and all this kind of stuff. He's talking about viscoelastic matrices in the universe, and that is something falls down into a minimum. Viscoelastic might give way a little bit from the gravity deforming the viscoelastic, and then as it gives down into another minimum, and how that movement could actually account for the way that particles came together to start to build the universe. But that then he ties that all into the idea of music and guitar strings and just all this stuff, which he made 5 videos explaining the theory, and each video is an hour and a half long. And I watched all 5 of them several times before I had the conversation with him, because I wanted to really understand the theory. I don't understand it well enough to articulate it, obviously. But it is based on the idea that of material being viscoelastic. So I was trying to understand really what viscoelastic is. But it never occurred to me that it had something to do with viscosity.
Conceptually related to each other, not necessarily identical things. But yeah, no, that I have to look at that.
But then it would be very vulnerable, or not vulnerable, but susceptible to temperature changes.
Yeah. Well, because one of the things to remember, which is a little weird, is that temperature is an indirect way of measuring the energy level of something, right? So the hotter something is, the more energy it has, and then the more that the molecules are moving, elementary part, I mean, atoms or molecules, depending on what it is that you're talking about.
So temperature is an indirect way of measuring.
Well, I guess it might be direct, but
Of measuring what?
Energy level,
Okay.
right? I don't know if it's quite indirect, actually. Let me think. Well, we give it a degree units wise. You'd have to play with it. So not quite sure if indirect or direct is a better way to say there, but when you're talking about temperature, you're talking about a certain type of energy that things have, right? And that's like we kind of see this in like diagrams and graphs of energy, of temperature, right? Where it's like the molecules are moving a little bit, and then the molecules are moving more and more. And we were already talking about this with gases. And so that's what temperature is representing when we're using it to talk about things. And so discussions about heat death and things like that have to do with stuff moving less and less, like you were saying, over time as the energy is kind of just distributed and spread out and things like that.
Well, so, okay, so when you're talking about adding energy to something, it seems to me like plugging a refrigerator into the electrical socket, you're adding energy.
Yes, you are.
But then things are cooling down rather than heating up.
Right. And because what you're actually doing in a refrigeration cycle is you're heating up the outside. So like refrigerators, air conditioners, and all of those things, they're always heating something up. You don't cool things down. You heat up other things. And when you're heating up another thing, you're pulling the energy out of the place that you want to cool down. So everything that we're doing when we're using energy to like make something hotter or colder, we're pushing energy, but we push it in one direction or another. And so like the refrigeration cycle basically plays with phase changes and pressures so that you can get something below a certain temperature to be able to push energy into it from the place that you want to cool down, make it cooler, playing with pressures, PV, nRT, that type of thing, right? So you move the temperature down while keeping the total energy of it kind of steady, and then you turn it into, and then you transform it into a different place where then you push out the heat into the environment. So like if you go to, every refrigerator is making heat, it puts more heat into your kitchen. Every air conditioning unit dumps more heat into the environment outside of where you're cooling. We're always like losing energy basically because of the electrical energy. Every time energy transforms, you lose some of it to the transformation
because of
process.
energy conservation. So if you're taking it out someplace, you have to put it someplace else.
Yeah, and then in real life, there's always inefficiency, just like there's always friction or there's always something. So you're always losing. It takes more than it would theoretically need to take if the equations were perfect. And that's the cost of doing life in the real world. Yeah.
Okay, so well, let's get back to the gauge blocks.
Yeah.
Because
that was a fun tangent.
One of the things that he shows a lot of different measurement tools. You could use a ruler, obviously, and the ruler has lines on it. And but even the lines themselves have width.
That's right.
So you have to know precisely what place on the line it would be in order to make a more perfect measurement. Then you have calipers, and calipers work by surrounding the object, and then that makes a measurement.
Yep.
And that is susceptible to the pressure that you put on or the way that you're
right, because the teeth of the caliper can deform depending on how hard you push them.
Right.
And so then that can be imprecision in your measurement as well.
Right. So then he says, if you need absolute accuracy, which is never going to be 100%, but you want to get more precise, you have to measure not empirically, but comparatively.
Yes.
And that statement started to blow my mind.
Yeah.
In terms of the implications of it at all the levels of reality. So I wondered what that made you think about.
Yeah. So the thing about it is you're always doing that. It's just you're hiding it when you're measuring directly, right? So he talks about surface plates, these ceramic blocks that you get certified within a certain flatness. And he didn't talk about this, but one of the things that we do is you have to get your surface plate re-inspected and re-certified at a regular basis. So at my old company, I think we did it
Surface plate
every,
would be the surface upon which you are doing the measurement. You're
that's
using
correct.
this as your substrate for doing the measurement.
So yeah, so you treat the surface plate as if it's a perfect plane,
Mhm.
as if it's this ideal, only to like perfectly flat plane against which you can measure things. Of course, in real life, it isn't perfectly flat. It can be such that the tolerance is negligible compared, you want it such that the tolerance of the flatness is negligible or so small compared to what you're actually measuring that you can ignore it. And that's, wow, that's actually really well, I think that that's something like really important to realize. That's always what we're doing with measurement, is you want the imprecision of your measuring tool or the technique that you're using, you want the tolerance of that to be negligible compared to the thing that you're measuring to.
So everything which is more fundamental, everything that goes down fundamentally to the more fundamental levels has to
Yeah,
become more and more and more and more precise as it goes
exactly.
down, right?
Yes. Yeah, exactly. And that's what we experience. The equipment that makes the machines that are more precise to make the parts that are more precise has to be more precise in order to be able to produce that equipment. And that's where it starts to become extraordinarily expensive to make these types of equipment and to make these types of parts. But so the surface plate is flat within some amount of microns, let's say, right? Millionths of a meter, and or thousandths of a millimeter. And is as long as that number is small enough, then when you're measuring, you don't have to account for that tolerance in what you're measuring. So and it needs to be smooth, and that's why it gets requalified. So there are tools that there are people who come basically and do a certification on your surface plate where they come and they measure it against itself. Is it as flat as it's supposed to be, or is there more variation in the flatness? And they're measuring these very, very small measurements, and then they'll do a lapping or a grind or like a refinishing as needed. And that's also why you kind of want to protect your surface plates. So you'll have covers for your surface plate so stuff doesn't get it dirty, because being dirty can cause it to not read properly. Or when you're setting things on top of it, you don't want to bang things into it, because the damage that you're doing can cause it to be out of spec and not able to serve its function properly by being damaged or deformed. And so basically what you're doing there, and like at our company, we use steel gauge blocks as well all the time. For the shop floor, you use steel because it's more durable and more reliable, and it's not going to break as easily as ceramic, and
Well, and
that's
it's
why
the
you use
same
it.
temperature as the material you're working with. So you don't
True.
have to account for temperature differentials as much.
As much, always as much, because each alloy is going to have slightly different coefficients of thermal expansion. But once again, those can become negligible where you can ignore them. They still exist. There is still a measurable amount if you get precise enough, but it's so small as to not impact the measurement that you're taking. And that's actually why I really like this term negligible, because negligible in the way that I use it means it exists and we can ignore it. It exists, but it's so small or so insignificant that we don't have to account for it in the specific context that we're working within. But it still exists. It is not non-existent, right? And so even in a surface plate, even in the most flat surface plate at the most precise, metrology lab in the world has tolerance in its peaks and valleys and its top and bottom, in its flatness. Its flatness is not the ideal plane that has no thickness whatsoever. It's only X and Y. There's no Z. There's always a Z, even if it's one molecule or half a molecule, like whatever your precision that you could possibly get it to. Even if it's the vibration of the molecules themselves, because they have energy and they're not at absolute zero. It's that there's something there which can never completely be eliminated, but it can become negligible. And so what you're doing is you're establishing, though, this plane as if it's perfectly flat. You're treating it as if it's perfectly flat. And then you measure against that in the Z direction typically is one of the main ways that you do it. At our company, we used a lot of height gauges, which are basically stands that have gauges like the one that Adam used in his video, but typically we would measure to the thou, would be precise enough for what we were doing. And so you're measuring against the surface plate up to that. So you're setting your plane and you're comparing the height from that plane from one side of your component, which is theoretically flat on that plane. And of course, there's imprecision in that. It's rough, the surface of the component that's resting on the plate. But you treat it as if it's flat, and then you measure against that for repeatability. And the thing is, when you're using a ruler or when you're using calipers, you're doing the same thing. It's that you're treating the edge of the ruler as that imaginary perfect plane. It exists. You're not measuring directly. You're implicitly making the end of the ruler this perfect plane that is the same thing as that surface plate, and then measuring a distance from that perfect plane. Or on your calipers, you're taking the piece that's on the outside, the fork, and you're treating the surface of that as the perfect plane and then measuring to it. So it's not, you're never measuring directly, actually, in the way that he
You can
describes
never
it there.
get away
But
from the standard.
that's right. You're setting this ideal plane somewhere
Yep.
with some imprecision and then measuring off of that to something else. Every linear measurement works that way, no matter what. But it revealed itself to Adam, and it reveals itself to people that work in measurement and metrology when you're working with a surface place and with a single dial indicator in a way that is hidden when you're using something like calipers or a micrometer or a ruler. And I think that that's really true.
So let's play a little bit with these
Yeah.
two words, with the word ruler and the word standard.
Yes.
I find very interesting that the words that are used around measurement are words that are also used in the polity.
Yes.
Right?
Yes.
So we have a ruler, and it has notches on it.
Yes.
And in ordinary measuring, a ruler would be enough to tell you whether or not that you're within tolerance, or but for more precise measurements, you have to have a standard. And you have to measure to the standard.
Right.
So I got thinking about this word standard and how in some of the old biblical language and old literary language, the standard was the flag that was carried by the standard bearer going out in front of the army and carrying the standard. And so in some way, the standard was an identifying feature of this community. This community was gathered around this standard, saying, we are willing to die for this standard.
Right.
Right?
Yes, it's the thing that unifies. It's what makes unity. Right. And I think that actually that it works really well too, because when you're doing these measurements, you have to, the standard is the thing that makes it so that all of your measurements are unified and they're brought together to be one thing. Every ruler, every gauge block, everything is measured against the standard, and then it's judged against that standard. That standard is what makes, what provides the unity. And that's absolutely correct. And that's so fascinating. I was talking about flags and standards and standard bearers on my recent trip to Korea, and we were looking at stuff there. And it's so fascinating because I remember being young in high school or junior high age, being like, why would you ever want a soldier that's holding a flag? That's so dumb. It doesn't do anything. There's no value in it. And now, twice as old and just a small amount wiser, I realize like it's what provides the unity. Without it, it's just a bunch of people. And with it, it becomes something more. There is this level up that it exists. And I really think too, you're onto something with this word ruler too. The ruler is the one that is above, but also there's a certain sense, especially historically, where the ruler is the one that should be the ideal. It should be the example. It should be the one that you're measured against. We should all want to be more like the ruler because the ruler is more good, more ideal in some sort of way. And we're missing that in today's world completely.
Well, but then the ruler is
Yeah.
also subject to the standard,
That's right.
right?
Yes, the
And
ruler is
so there is this built-in
yeah.
hierarchy in the
Yes.
world.
Yes.
And when you just said that about the standard is what creates the unity, that made me think about how every single object in the world, when Jordan Peterson or Jonathan Peugeot or John Vervaeke talk about objects as being a multiplicity that is actually a unity.
Yes.
But if we think about manufactured objects in the world, which there are a lot, there's the door and there's a painting and there's a cup and there's my pen. And so this
created
is
objects
by many different machines.
Yes.
And it has plastic in it, which is manufactured, and it has metal in it, which is manufactured, and the steel center and the spring and all these different things. And then they have to fit together.
Yes.
This is a unity made up of multiplicity.
Yes.
This particular unity made up of multiplicity is based on a certain set of standards that were used for this machining.
Yes.
And maybe if I had a much more expensive pen, one of these fancy ones that comes in a beautiful satin box, right?
Yeah.
That one is based on a different set of standards. And
That's
so
right.
it has a different value.
That's right.
Different monetary value. And things that are handmade have different standards that they're based on. And they also have a hierarchy because there are things that are very naive, and then there are things that are very sophisticated that are handmade. And so a computer is based on a different kind of set of standards.
That's right.
Every single thing in the world is unified, is able to come together and fit together because of the kind of standard around which it's operating.
That's right.
And then there has to be some standard around which this whole thing is unified, right?
Yeah. And
so the standard has to be the most fundamental. Jordan Peterson's always talking about that which is most fundamental is that out of which most things grow.
Yes.
Right?
Yeah. Right. And that, like, as people who read the Bible and believe it, as people who have lived and experienced the reality of God's power in the world, that is God. And not only is that God as agent, like doing things, but I really, the concept of God as arena that Paul really put me onto or explained in a way that I understood it. God is the one in whom we live and move and have our being, the one who is the source of all being, the one who is the place in which every ideal, every standard, every good thing finds its origin, source, and home. That is God. And he is the one that makes all of this even make sense. Like, imagine that you really believe that it's all at the most basic level. The standard is randomness, chaos. How can that standard, using all of the description in the way that we're talking and thinking about it, how could that standard possibly make the world that we find ourselves in? There's no, it's inconceivable. It really reinforces to me that there has to be at foundation, at the most fundamental level, an order or an organizing something or other in the way that the world itself is even made and brought into being. And as it says in 1 Corinthians, God is a God of order, not a God of chaos. And so it just really combines together with that for me. Absolutely. And yeah, when you're talking about pens and different things like that, there's drawings, and there's always a drawing, and the drawing is always perfect. In GD&T measurement, in the way that you make drawings, you draw it as it's 4 inches exactly, and then you give the tolerance somewhere else. And every pen is going to have the most minuscule and maybe undetectable differences, even though it's all unified under one standard, which I think is
Did you
so
learn this in
fascinating.
school when
Oh,
studying
hold
the
on
universe?
just a second.
What
Sorry.
the physicists
I was trying to queue up a video to show you.
Yeah, that's
And the
okay.
sound came on immediately. I didn't mean to interrupt you at
That's
all.
okay. No, that's
Um,
wonderful.
Yeah.
I want to finish that one. So
Yeah,
every pen
absolutely.
is made off of this drawing, right? It's made in the image of this drawing.
Mhm.
And every single pen is going to have, at a molecular level or at some level, difference. There will not be, they'll be identical at a certain level of analysis, at a certain level of review. They're the same.
Mhm.
But when you get into the detail, you'll find differences, always, because that's how actual manufacturing works. We make, like, as someone who works in manufacturing and sells the same part to customers, I can still know, I know that they're not identical to the molecular level. Like, it can never be in the real world such that they're exactly the same. And I think this is also true of humans. I think one of the things I learned several years ago when I actually started going to the church that I currently attend is how the creativity of God is expressed in all of the different people that he has made. And how it's one of the most beautiful things because we are all made in his image. There is a level of analysis in which we are all the same, made in the image of God. And yet, when we experience each other and know other people, we are all different in some way from one another. And that is a beautiful, beautiful thing. So anyways, that was one of the
That's the
questions.
sacred side of individuality, right? I mean,
Yes.
we have the toxic side of individuality that says, I'm
Yes.
individual, I can do what I want and I don't
Yes.
need anybody else.
Yeah.
But the sacred side of individuality is you are an
Yeah.
individual.
Yes.
And that is a beautiful thing that you are
Exactly.
completely unique.
Yeah.
And it's a matter of looking outside of ourselves and seeing what individuality really means.
Yeah.
And then to also see that what community really means is for all of these sacred individuals to come together,
Yes.
right? And make something more beautiful than this.
Yeah, exactly. And in relationship with one another, combine into a higher unity, right?
Yeah.
Yeah, absolutely.
Gathered around a standard.
Mm-hmm.
So the reason I was bringing up this video that I wanted
Mm-hmm.
to show you is when you were talking about it can't be random, there has to be a rule. And so then that made me think about this video. So I'm just going to bring it up real quick and we'll take a look at it.
Did you learn this in school when studying the universe?
What the physicists have discovered is that the fundamental parameters of the universe, the strength of the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, the force that is driving the expansion of the universe called the cosmological constant, the masses of elementary particles, the mass of the quark, for example, the speed of light, the many different fundamental parameters are just right. All these things rely on numerous elements falling within narrow tolerances of one kind or another. All of those systems that I just mentioned have one thing in common, and that is that they were designed by intelligent agents.
Did you learn this in school when studying the universe?
I love Stephen Meyer so much, partly because I think that he provides a look from inside the scientific materialist. He provides an approach and an angle, pushing people to recognize God's plausibility from within that frame in a way that's so helpful for many people. Because a lot of the people that are going to be at the conference, the meeting face-to-face conference, they're not in that frame. They don't live in the scientific materialist post-enlightenment Western thought frame anymore. If they ever did, they live in a world that is older, that is more relational, that is more connected, that sees things differently and knows that there's more out there because of their experience and because their eyes have been opened to see it. And that's awesome. And helping people get into that frame is useful and wonderful and good. And I think it's one of, like, Jonathan Peugeot in particular's greatest strengths is helping people make that shift. But Stephen Meyer is not making that shift in the way that he's approaching any of this stuff. I can't speak for his personal experience, but he's staying in that mode and still pushing and poking and forcing and confronting in a way that is immensely valuable. And I think that his ability to articulate well in that short clip and in other places a summary of the fine-tuning argument is amazing, because he doesn't even really explain it there because that's such a short clip, but the tolerances that he's describing, like we've been talking about millionths, or in the video that Adam Savage that we watched, he talks about nanometers, billionths of a meter. But in some of those constants that he's describing, it's like 10 to the negative 38 or something. I mean, it's a billionth is 10 to the minus 9. So it's just orders of magnitude and orders of magnitude and orders of magnitude more precise and more amazing when you look at the actual the measurements and the things that they've discovered. And yeah, anyways, I don't need to harp on that anymore, but I agree. It is very important to recognize.
Well, so the bottom line of all this, so that we can wrap up, is that absolute precision is not possible on the human scale.
Yeah.
Obviously, it's possible on God's scale, but it's not possible on our scale. So that means that to some extent we have to become, maybe comfortable is not the right word, but we have to become willing to face uncertainty.
Yes. Absolutely. Actually, I have a couple of different thoughts on that, the way that you said that, which I really appreciate. So in Adam Savage's video, he describes what he's how he understands his own point of view, which is a specific word that he's using to mean his worldview, really. He describes it as a cosmology of machining, which I thought was so fascinating. The understanding of, because cosmos is the universe, it's all that is. And so it's his understanding of all that is in regards to machining, but then he's extrapolating it out, which is super interesting. And he said, all measurement is a compromise of circumstance, which I also thought was beautiful as far as a summary of so much of what the video was about.
What did that mean to you? Because I heard him say that it's a compromise of circumstance.
Right. So what I understood is essentially that it goes back to part of where we started, which is there's the personal. So the circumstance is the context, or it's the relationships between the thing being measured, the person measuring, and the environment within which it's being measured, both physically and otherwise. And so, because the thing is, you don't measure something unless you want to know what it is, right? So there isn't measurement outside of someone wanting to know. And you might say, well, I just measured it for no reason. Just to see it or something like that. But there was some agency that went into that. You know what I mean? Like measurement, as I said earlier, doesn't exist outside of agency. Measurement only exists within agency. And this goes back to where there's always a person measuring. And that is one of the big things that science is missing. And I don't know necessarily that we want to go too deeply into this, but I wonder sometimes if measurement and perception, how they're related, because measurement is a type of perceiving, or it's at least mediated via our perception. But when we're doing comparisons,
we got to talk about this then, because this is a cool conversation, because this goes down to J.J. Gibson's work on the ecology of perception. And I think we could have a very valuable conversation about that. So keep going.
Yeah, well, I'm curious to read that and look at it more closely, because I'm not familiar with that, but I would love to, because the question of perception is one that I still struggle to properly wrap my mind around, because we see things with our eyes and then we see things with our minds, and those are the same in some way. We measure things with instruments in a lab, but we also measure other people, and we measure our experiences against each other and against some standard, like we were talking about before, of how it should be. And what are we doing? How are we doing that? What are we using? What is it exactly? It's something that I want to continue to think about, because I don't have my mind fully wrapped around it. But it's definitely interesting. And so that was just a little bit, but going back to the last thing that you said, which I really, really loved, which is that being comfortable, maybe not being comfortable, maybe being willing to accept. I do think being comfortable is the ideal. It's what we should be aiming at. I think the first step to getting there is being willing to accept it. At about 37.5 minutes, Adam Savage says in that video, there is no such thing as an actual measurement. And what he meant, and the way I would word it instead, is that there is no such thing as a ideal or perfect in the sense of without error. Because we use the word perfect in two ways. We use the word perfect to mean that it will serve the function that we want from it. They're a perfect couple, they're a perfect fit. It means that they work, right? Or it was the perfect timing, meaning it works. But there's another meaning of the word perfect, which is that it's ideal or without error or without tolerance. Because tolerance is error. They're the same thing. And so there's a certain amount of that we have to live with, because in reality, we will never get to an ideal or without tolerance or perfect measurement in our experience. And since that's true, we need to live with that uncertainty. I think that certainty is this word that has to do with the types of things that we know. Part of what Descartes has really firmly kind of proven, at least in my understanding, with his demon providing hallucinations kind of counterexample, is that we cannot know things without any doubt. We cannot know things with perfect and complete certainty in this world. There's always a counterexample that you could give, whether it's a brain in a vat or a demon causing hallucinations in your brain or whatever it is, of a way in which even our perceptions themselves cannot be fully trusted. And yet we must live in the world as if our experiences and our perceptions are true to the best of our ability in order to be able to make any decisions, in order to be able to put the next foot forward when we're taking a step. We have to believe that what we see is what's going to be there and what we will encounter. And so even there, we are living with, even if it's a negligible amount, meaning that we can completely ignore it, it never goes to a complete zero of amount of uncertainty in our lives. And I think that this concept of metrology and measurement can help us see that in a way where we'll say it's 12 inches and we'll ignore the tolerance and the uncertainty because it will still serve the function that we need. And it is, we know it certainly enough. And so there's this idea of knowing things certainly enough in order to act as if that's what they actually are, because they will serve that function, but not requiring of ourselves the elimination of all uncertainty before moving forward in the world that is necessary for us to live rightly in the world. And it scales up when you're going to be getting a new job, as something that I'm going through currently, where I'll be starting a new job next week, and there's so much uncertainty. What are my coworkers going to be like? What are my responsibilities going to be on a day-to-day, practical, minute by minute, hour by hour kind of basis? I have an idea. I've been told what it should be like. I won't know that until I'm there, but I need to step forward believing and trusting that it's going to be something that will work out, because first of all, I trust God. But even if you don't, you just need something like that in order to be able to even move forward into the potential and into the possibility, or else you're frozen and you're stuck and you'll never move and you'll never do anything. I think probably you could express this from an artistic standpoint. If you look at a canvas and you think, well, if it's not going to be perfect, I don't want to do it, you'll never make anything. And yet you have to go forward and start to make the art, believing that whatever imperfection there is that will exist because it's something that exists in the physical world will still be a part of the whole that you make that will be beautiful.
Yeah, there's so much in what you just said.
Mm.
So much riches there. And I want to flip it just a little bit and say, what if I decide to live my life without accepting that uncertainty exists? Let's just say I decide to live my life as though I'm certain of everything.
Yeah.
I know it all.
Yeah.
That is Jordan Peterson's description of Satan in Milton's Paradise Lost.
Yeah.
I don't need anything outside myself.
Yeah.
I've got it all figured out. I have no uncertainties. I can just move ahead as though I'm correct about everything.
Yeah.
Well, okay, that's not taking into account the environment in which I live, all the people that are around me, all of the possibilities that could occur in the future.
Yes.
It's all that is taking into account is me.
Yes.
And the biggest problem with that is that the only place that you can meet with the transcendent is at the edge of your knowledge.
Yeah.
Where you are no longer certain.
Mm-hmm.
And then you have to voluntarily come up against that uncertainty and trust that being is good.
Yes.
And trust that, like, you're taking a new job. If you couldn't trust that in some way being is good and that being itself will meet you at the needed moment of uncertainty in this new job, how could you possibly face it?
Yeah,
It'd be
exactly.
so terrifying.
Yes,
right?
absolutely. Yeah, and that's beautifully said. Yeah. Yeah, one of the things that my family has dealt with me and close friends as well, is this discussion of measuring other people's reactions to things or relating to things as either too certain or not certain enough. People that are too certain, it is pride, and it is not good. When you're more certain than you should be about something, it can lead to all sorts of pain and suffering and harm and damage to those around you, and to yourself. And so it's something to be cautious of. Don't be more certain than you ought. But then that also comes with it's being the right amount. It's being the appropriate amount. It's calibrating. It's not missing the mark on either side, but walking the narrow road. It's so hard, but not being certain of anything is no way to live either. If you can't be certain enough to ever take a step forward, then you become nothing. And so
that comes from not having a standard.
Yes.
If you don't have a standard, then you can't be certain of anything.
Then you can't be certain enough to do something, right?
Yeah.
Yeah, because enough means we're within tolerance. The amount of uncertainty has reduced to a point that I can live with it, and then I'll go forward, right? And so, that's how we ought to live.
Well, let's champion your move forward into this new job.
Yeah.
And after you kind of get things under control a little bit, my husband used to always say, it'll be the first 6 months.
Yeah.
Every time he'd get a new job, he'd say, don't expect to see too much of me for the next 6 months.
Yeah.
Which is fine when he's in a job for 8 or 9 or 10 years. But there was a period of time during all the ups and downs of the .com boom and the .com bust and all of that kind of thing, where he was changing jobs every 6 months. So,
yeah, that's so tough.
Yeah, but it's been good now. He's been at the same job for a long time. So anyway, I'm excited about your new job. I'm excited to talk to you again in 6 months or so. And maybe our topic then will be how perception and measurement and uncertainty and all those things come together around J.J. Gibson's ecology of visual perception. And I'll send you some material. I'll also put it in the comments for people to look at.
Awesome. Thank you so much, Karen. What a great joy and pleasure it has been.
This has been a blast. Absolute blast. Way more fun than I expected it to be. I hope everybody else has as much fun as we do.
Yeah.
And another reminder, if you're going to be near Olympia, Washington, second week in September, sign up for the face-to-face conference.
Yeah.
And I will put a link for that in the comments, in the description section as well.
Awesome.
Heidi ho. Bye-bye.